In this video, I would like to describe the 4 field grading methods and explain the principle of cable termination. So what is field grading, first of all? Field grading is a method we apply in high voltage when we have a place where there is a too high concentration of electric field strength, and we want to decrease that concentration. That could, for example, be if we have a cable, and that cable is ending rather abruptly, meaning that it's just terminated here, and we want to make sure that the electric field here isn't too high, which it would be if there's no field grading applied, because from the basic equation here of the electric field strength, we know that it's proportional to the negative gradient of the voltage, meaning that if the radius here is very small and there is a large change in the voltage, then the electric field will be high, which is the case here. So in that case, we want to apply one of the field grading methods, and there are 4 methods I want to go through. There's electrode grading, Epsilon grading, condenser grading, and resistive grading. And we're going to start by looking at electrode grading. The most simple form of electrode grading is when we have, again, a termination here, very sharp termination in this case, and then we apply some material that could, for example, be fluoride around here. So if we do that, what happens is that the electric field will distribute itself in a more beneficial way. A more defined example is, for example, cable termination, where we apply a stress cone. So let me draw the conductor, and I'm going to draw it a bit more detailed. So we have some insulation layer here on the outside of the conductor, and then we have another layer, which is the semicon layer, is grounded. So let me draw a symbol here. So this one is grounded, sitting at 0 volt, something like that. And this one sits at a high voltage potential. And what we instantly see is that there is a large change here between the grounded semicon layer and the high voltage conductor. So there's a large change in the potential over a small radius. So the change here to here is pretty small, and we want to make sure that the potential can drop over a larger distance. That is the purpose. And when we model this as smaller capacitors. So we have some capacitance from the semicon layer to the insulation, along the termination here, just before the termination, and along the cable. And we have some capacitance from insulation to the conductor. And the idea is to stretch this capacitance over a longer distance, so that the drop in potential will be along the surface over a larger distance. So what we do essentially is that we stretch this layer here, sitting at a 0 volt potential. And when we do this, we are essentially creating some capacitance between the conductor and ground. So instead of having a large voltage drop over a short distance, we have the same voltage drop, because we do want to go from a high potential to a low potential, meaning that we have the same voltage drop, but we have it over a larger distance. So this is the distance here, which we are increasing. And what happens when we do this is that the gradient is more constant. We can also illustrate this on a graph where we have the distance to the termination here on the x-axis, and we have the potential up here on the y-axis. If we don't apply electrode grading, the potential looks something like this, meaning that there is a rather abrupt change in the potential from the semicon layer to the cable. So this is without. However, if we do apply the electrode grading, the gradient will be more constant, and in that case, the electric field will also be more constant, and the drop will not be as high here on the edges, which is beneficial because then we don't have any partial discharges. So the whole idea is to make sure that there is some cone that can stretch the potential drop along the surface, minimizing the concentration of this electric field strength. Another method is epsilon grading. So let's draw some materials here. This could, for example, be the semicon layer, kind of insulator. So let's have this material be with a permittivity of 2. And now we are applying epsilon grading. So when we apply epsilon grading, we want to distribute the field more evenly and make sure that the field lines doesn't bounce up around the edges. But if we apply epsilon grading, what we do is that we add some material around, And that material has a different permittivity. And if we want to decrease the electric field strength in this material, what we do is that we apply a material with higher permittivity. So we apply another material here with epsilon of 4. And what happens is that by the reflection law, the lines bend away from the edge. So instead of having the equipotential lines here to crowd around the edge, they will bend away. We can also write it with the equation here that we know, stating that the normal component of the electric flux density at the boundary is equal. So what do I mean by that? I mean that the normal component of the electric field here going in of the flux density should be the same as each sides of the boundary. So this is the N1 and this is the N2. And these two components of the electric field across the boundary should be the same. We can also rewrite them here in terms of the electric field strength. So E1 times epsilon, let's just call this 1, this one 2, epsilon 1 is equal to, this is the normal component, is equal to E2 n times epsilon 2. And if we rearrange this, and with the purpose of decreasing this electric field strength, the normal component of the electric field strength on the second medium, what we see is that the electric field strength of the second medium, E2n, or the normal component of that, is actually getting lower by applying this epsilon grading. 2n divided by epsilon 1, times epsilon 1 divided by epsilon 2. So what we see is that we actually decreasing the normal component at the second medium here by a factor of epsilon 1 over epsilon 2, in this case by 2. So this is how we can apply epsilon grading by choosing materials with different permittivities. The next kind of field grading is condenser grading. And the reason that we apply condenser grading is to make sure that there isn't a too high difference in voltage between 2 points. So we add some capacitive layers to distribute the potential more evenly. That could, for example, be if we have a high voltage cable that we want to feed into a transformer. So this is the transformer here. I'm going to write C for transformer, and this is the high voltage cable. So this has high potential, and this sits at 0 volt because it's usually grounded outside of the transformer. And then we see that there is a large difference between this potential and the 0 volt. So there can be flashovers in worst case. We can have flashover in worst case between these 2 points. And that's not something we want. So how can we prevent that? We prevent it by adding some capacitive layers from the high voltage cable to the transformer. So we add some capacitive layers here. And what you see is that the layers decrease in length, but increase in radius. So we have a radius here along this axis, and we have a length here. We have a length here along this axis. And we want to keep this ratio between the length. So we want to keep this ratio between the length and radius somehow equal, somehow constant. And if we do this, that means that we have the same capacitance across each of these layers. So let me write the equation here. So for some charges, if we have the same capacitance, then we have the same voltage drop across. So what we do is that we keep the voltage drop constant again across these layers. So instead of having a huge voltage drop from the high voltage cable to the transformer, we have almost constant voltage drop across each of these layers, preventing the flashover. So this is the purpose of condenser grading. The last form of field grading is resistive field grading. And what is meant by that is, as you might have guessed, that we have some resistance, R, and that resistance will cause a voltage drop because from Ohm's law we have that the current times the resistance equals the voltage, meaning that if we have some resistance, then we can have a voltage drop. And the idea is to apply some resistive material at a place where there is a large difference between 2 potentials, so we can distribute the drop in voltage over a larger distance, and it's not as abrupt. An example of this can be for a generator. So we might have a high voltage generator, and I'm drawing a stator here of a motor. So I'm going to write S here for stator, and the stator sits at 0 volt. So we have 0 volt here. And then we have a stator bar. So this is the stator bar. And then we have some insulation materials. I'm going to draw that in blue here along the stator and on the other side. And as before, there's always some capacitance along here. So we have some capacitance along the insulation material to the conductor. But we see the problem, and the problem is that from here to the 0 volt to here to the high volt, we have a pretty large difference between the two potentials. And when we have this large potential between the two differences, we also have concentration of the electric field, which we don't want. We want the distribution of the potential to be evenly distributed along this distance here, And to make that happen, what we can do is that we can apply some field grading method. In this case, we are applying resistive field grading. And what we are doing is that we are up here, we are applying a layer of resistive material. And this resistive material has some properties that are pretty interesting. It's nonlinear, meaning that it's not the same resistance that it has depending on the electric field. And that is pretty smart because we have a high concentration here near the termination between the stator core and the stator bar here, conductor. And at this termination, the electric field is pretty high. So what we would want is that the resistive material to be low, so we can have a high current and a voltage drop here. But when we go further away, the electric field decreases and the voltage drop also decreases, meaning that we will have a more evenly distribution by applying this kind of resistive material along the stator bar here. So in this way, we can use resistive grading to create a better distribution of the voltage along these kind of surfaces. So these were the 4 different field grading methods. We had electrode grading, where we shape the electrode, for example, adding a toroid around the electrode to distribute the field better. Then we had epsilon grading, and epsilon grading was when we had 2 different materials at a boundary, and we wanted to improve the electric field in one of the materials mediums by having different permittivities. We can do this, and this is called epsilon grading. Then we have the third method called condenser grading, and that is, for example, we had the cable going into a transformer, and then this bushing had layers of different capacitance distributing the drop of voltage better instead of going from 0 volt to high volt. And the final was the resistive grading, where we applied some resistive material with a nonlinear reaction to the electric field, meaning that the current would be higher where there was a high field strength and cause a voltage drop proportional to that high field strength, and then lower when we went away from the high field concentration. So these 4 methods can be used